Log on, tune in, find out. Another good idea from Cambridge.
Arend Bayer from the University of Connecticut, ability conditions for the local projective plane.
Okay, so thank you very much for the invitation to speak here. So what I'll talk about is now a slightly old work which Emanuele Macri, 1.5 years old now, but I thought it was very fitting for this program since it connects very modern questions with more classical questions. And so maybe let me start by just saying, explaining the words in the title. So the setting is that X is the total phase of the line bundle -3 on P2. And inside here I will look at the derived category of sheaves.
Arend, is your microphone turned on?
No, it should be on. Thanks. So inside here I have the derived category. I look at the derived category of coherent sheaves supported on the zero section. And then I will consider the space, so I will just denote it by stab of X. So this is the space of bridge instability conditions on D. And I will give an idea what bridge instability conditions are. But before that, I just wanted to put up one slide, so this won't be a slide talk, there will be just one slide. So the just picture with some of the questions this space is related to. So I mean so one thing I will talk about quite a bit is about the questions about slope-stable bundles on the projective plane, namely the question for which Chern class does there exist a slope-stable bundle on P2, and so here DLP stands for this work in the 80s from Drezé and Le Cotier. It's also closely connected to exceptional bundles on the projective plane and the theory of mutations, so the Russian school in particular. In this case, there's a paper by Gorodensev and Rudakov. Then it's connected to mirror symmetry, and in this case, this means to the moduli space of elliptic curves with gamma 1,3 level structure. And finally, it also has to do with the birational geometry, or more precisely, the lack of birational geometry of X. So there are no birational Calabi-Yau, no Calabi-Yaus birational to X. And in my talk, I will start out here and hopefully have time to walk through all these areas. And so let me start by describing. So let me start with mirror symmetry and describe two of our main theorems, and then explain how they are related to these to these other problems. And so before talking about mirror symmetry, so I should just say what the mirror family is. I mean, the mirror pattern of one variety is always a whole family, and in this case it can be seen as the universal family of elliptic curves with gamma 1,3 level structure. So here gamma 1,3 is the subgroup of SL2Z of matrices that are congruent to 1 star 0 1 modulo 3. And we really have two theorems that are related to mirrors, to this mirror family. Namely, the first one is almost describes the group of autoequivalences of the derived category. So we identify a subgroup out dagger, so of the derived autoequivalences of D. So I mean, probably this is really everything, but we can't prove that. And we identify this to be gamma 1,3 cross some trivial part, so then they are just shifts other than gamma 1,3, they are just shifts and then automorphisms of X, or more precisely of a formal neighborhood of P2 inside X. And really the main reason I want to state this now, since this allows me to state the second theorem. So I mean, somehow this is in a way this is a typical mirror symmetry statement, because it identifies the mapping class group of the mirror family with a subgroup of the group of autoequivalences. And that's, I mean, that's in conjectural form due to Kontsevich, and I mean, there are many examples of this that have been studied by Seidel-Thomas or Hoyer, where theorems like this have been proved. But here one can also make a more geometric statement, namely, there's the following statement. So there is an embedding of the universal cover, so M gamma 1 3 twiddle into the space of stability conditions, and it has the properties that it's gamma 1 3 equivariant. So gamma 1 3 acts on the left-hand side as the group of deck transformations, and on the right-hand side, just via this inclusion, as the group of autoequivalences. And in coordinates, so I'll say later what this means, in coordinates given by periods of a meromorphic differential form, so of a meromorphic differential form on C gamma 1 3. Okay, and so now I'm going to explain how these two theorems really come from the theory of arise from the theory of slope-stable bundles and exceptional bundles on P2. So let me say a little bit what a Bridgeland stability condition is. So Bridgeland So there are always two ingredients. One is just a linear algebra ingredient. So it's a pair Z comma A, where Z, so this linear algebra ingredient, is just a map from the K group of the derived category, which of course in our case is just Z to the 3. So it's a group homomorphism to the complex plane. And the second ingredient is, now this is the categorical ingredient, so I have to identify a subcategory of D, so this is an abelian subcategory. So really the technical condition is that it has to be the heart of a bounded T structure, but I'll explain later really how to construct this A. And these have to satisfy two properties. And the first one is a positivity property, and this positivity property is actually quite subtle, and this is really where the questions about slope-stable bundles come from. Namely, it says that so when I have an object E in A, then Z of E has to be in the semi-closed upper half plane. So I take the upper half plane union the negative real line. So let me add a picture. So I take the upper half plane and add the negative real line, and then I can use the phases of this complex number as a replacement of slope. So once I have this, I automatically get the notion of stability in this abelian category. So just by saying an object is stable if and only it has no sub-objects that lie further on the left that have higher phase. And so the second condition is that Harder-Nora-Simon filtrations exist. Okay, and I mean the example that one should always have in mind for this is when X is a curve, then I can take I can just take to be coherent sheaves on X, and I can set Z of E to be minus the degree of E plus I times the rank of E. And then I really get classical slope stability on this curve. But a similar construction won't work for higher dimensional varieties. So there's no bridge and stability conditions on higher dimensional varieties where I just take coherent sheaves. And now, how could one study the space of all such stability conditions? Well, here we basically follow a strategy by Bridgeland for K3s. So maybe at this point I should say that. So I mean, Bridgeland actually has a paper where he describes an open subset of the space of stability condition purely in terms of exceptional bundles and mutations, and but he only sees an open subset, and some of our methods are in a sense orthogonal, much closer to Bridgeland's method for compact K3 surfaces. And so the strategy says one should first look at stability conditions that are as closely related to something geometric that you could hope for. Namely, at least we want that skyscraper sheaves of points are still stable. So we assume that all OX in A, so here this is for X in P2. So we want them to be in our abelian category, and we want them to be also to have maximal maximal slopes. So in other words, I can normalize my central charge for those to be of -1. So something of -1 has maximal phase in this picture. And
That's what P2 has got to do with it.
so now I'm back to this case. So I'm back to I'm studying stability conditions of this category D.
But P2 is a sub-variety.
Yes, it's a sub-variety here as the zero section. And so here, I mean, I'm only looking at coherent sheaves that are set theoretically supported on this P2. So these are really all the skyscraper sheaves of points that are even in this category. And so I'm asking for these to be stable of maximal phase. And of course, since our K group is just Z3, this automatically forces Z of E to be of the following form. So it's minus churn 2 of E plus A times the degree of E plus B times the rank of E. Where here I really mean churn 2 and degree and rank as seen on P2. So in other words, I look at the push forward to a projective space. And so under this normalization, my central charge depends on two parameters, A and B in C. And you'll see immediately that this cannot work with coherent sheaves. So if you look at the imaginary part of this of CAB of E, and let's normalize it by dividing by the rank of E, then this is just the imaginary part of A times the slope of E plus the imaginary part of B. In other words, up to some linear parameterization, the height of this complex number is just given by the slope. And so in particular, remember our goal is to find an abelian category for which the Z of E lies in the upper half plane. So it's obvious that the imaginary part of Z of E is greater or equal to 0 if and only if the slope of E is greater or equal to minus the imaginary part of B divided by the imaginary part of A, and I'll call this constant B. So objects of big slope will automatically be in the upper half plane and satisfy these conditions, but coherent sheaves of negative slope will be in the lower half plane. So I will have to do something about them. And then there is a proposition by Bridgeland that again where the proof carries over with little change. that really tells us exactly how much we have to go away from coherent sheaves and into the derived category. Namely, it says, so with the central charge and the property, so still under this assumption that skyscraper sheaves of points are stable of maximal phase, then the statement is that A necessarily is of the following form. So I look at a subcategory of coherent sheaves. I will define two subcategories of coherent sheaves. So it's the torsion part. This is generated by torsion sheaves and by slope stable sheaves. Of slope bigger than this constant b. So what I mean by torsion-free and torsion sheaves and torsion-free sheaves, of course torsion-free means relative on the P2. So as sheaves on P2 they are torsion-free and slope stable, slope bigger than b. And by torsion sheaves I mean sheaves with 0 or one-dimensional support. And then there is a second subcategory where I just take slope stable sheaves of slope less than or equal to b. And these brackets then mean that I take the extension closure. Okay, and then Bridgson's proposition says that A is necessarily of the form. So I take TB, so coherent sheaves of big slope. I take coherent sheaves of negative slope and shift them by 1 as complexes in the derived category. So this is now a subcategory of the derived category D. And again, I take extension closure with respect to the triangulated structure of D. But concretely, this really means that I'm just looking at two-term complexes. So complexes E minus 1 to E0. So that the kernel of D is in FB and the co-kernel of D is in TB. So it's really as close to coherent sheaves as you could hope for. And let me call this category AB. And so I mean when I shift objects by 1 in the derived category, then I'm multiplying all the Chern classes and so on by minus 1. And this means I really have solved this problem. So it's immediate that the following statement holds, so that if E is in AB, then actually did I give the central charge a name? So I want to then ZAB, so the central charge given by this formula has imaginary part greater or equal to 0. So in other words, I had the condition that it lies in this upper half plane union the negative real line, and I'm almost there. I just have to exclude that there are no objects on the positive real line. And to look at whether this condition holds, that there are really no objects on the real line, now I really have to look at slope stable objects. So I mean here in the definition of AB, the slope stable sheaves appeared. So hopefully this motivates a little that I have to ask myself the following question. So maybe I have to ask, so where can Z of F divided by the rank of F lie for F slope stable? In this category of coherent sheaves. Okay, and so I mean, of course, Z of f involves the degree in the second Chern class, and so it's quite natural to ask this question first with some reparameterization. Namely, instead, I'm asking, so what are the possible values of the slope of f and the discriminant of f, so which I, for this purpose, I normalize to be the second Chern character divided by the Chern 0 minus 1/2 the slope squared. So in other words, the discriminant really measures how does the second Chern character differ from the second Chern character of a line bundle with the same slope. And this is exactly this question that has been studied by Dressé and Le Portier. I mean, first there is the Bogomolov-Giesecke inequality, which in this case is really follows straightforward from Hürtelbuch-Riemann-Roch, that says that delta is greater or equal to 0. But Dressé and Le Portier made this result much more precise. And so what I'm going to draw a graph in the real plane of the possible values for mu of f and delta of f for f slope stable. So here in this direction I'm drawing mu of f and here delta of f. So I mean the first thing I know that there are no objects here in the lower half plane, and then what are objects exactly on the real line? Well, here of course they are line bundles of -1, 0, O of 1. And let's say we want to study stable vector bundles that have small negative slopes, so whose slope lies somewhere here. Then we know there are no morphisms from O to this vector bundle because this would destabilize it. But there's also no x2. So there's no x2 from an object to here because by their duality this would give a morphism from this vector bundle to O of -3, which would again be destabilizing. And so putting these together, we get that the Euler character, so if you have a sheaf F somewhere here, we get that the Euler characteristic between OP2 and F is less than or equal to 0. And of course, computing this with Grothendieck-Riemann-Roch immediately gives an inequality for the Chern classes. And what does this inequality look like? Well, it turns out there's a parabola like this. And then by duality, there's also a parabola going the other way. And of course, I can replace OP2 by these other line bundles that I draw here, and I get many parabolas like this. So again, what is the statement? The statement is that except for these line bundles, all stable objects, when I plot this number delta f, mu of f, delta of f will be above this zigzag line. And now, of course, I mean, whenever two curves intersect, there's something exciting happening. And indeed, here, I mean, these intersect at slopes, half integer slopes, and so they're actually bundled corresponding to these intersection points. And probably you can then guess already what they are. So they're the twists of the cotangent bundle. So here we have omega of 2, here we have omega of 1, and here omega, and so on. And then we can do the same argument starting with these twists of the cotangent bundle, and again get smaller parabolas looking like this. And it turns out that one can keep going. So here at the intersection points, we always get exceptional bundles. So exceptional here meaning rigid and simple. And I mean, I learned, of course, I learned the notion of exceptional bundles 20 years after Dressé Le Portier. came up with this name, and I always thought because the name comes from them being isolated in a moduli space. But I think originally probably the name came from this picture, so the Chern classes are isolated in this picture. They're the only isolated points in the when I continue doing this picture. So let me state the precise result. So, I mean, first to explicitly construct all delta of E, so all classes of exceptional bundles. And then they construct a fractal-like function, so that's given as the supremum of infinitely many parabolas like this. So I can keep filling in the intersection points. So there exists, I like to call it a fractal-like curve, although technically it's not a fractal. So curve delta of mu, such that there exists a non-exceptional stable bundle with invariance mu and delta, if and only if, so assuming these are rational numbers, of course, if and only if delta is greater or equal to this function delta of mu. So in other words, if I keep filling in this picture, then I'm getting more isolated red dots, and I'm getting this fractal-like curve, and all the other pointing to squared above this line will be the image of some slope-stable bundle. Okay, so what does this have to do with our question? So
So could you be clear? This picture, you're only drawing the interval between 0 and between +1 and -2. It goes the whole way.
yeah, I mean, it goes the whole way. It's
Right.
the
So this is
invariant,
sort of
yeah.
SL2. It's the upper half.
Okay, and I mean here, in a way, we've already identified the only vector bundles that could potentially cause a problem. the only objects that could potentially cause a problem are those on the real line, and these are exactly slope-stable bundles of slope equal to b. And or in other words, I mean, so I mean, let me translate this picture back to this question. So let me have point z, plot g of f divided by rank of f for f slope stable. Then this is basically the same picture, except that it's turned around, and instead of these horizontal straight lines, I have parabolas. So there's a parabola on which all the line bundles lie. And maybe I should also say so that here this function is delta equal to 1. So this is the parabola of objects with delta equal to 0. And then there is a parabola delta equal 1 here. And then this fractal curve basically becomes this fractal curve added to the parabola. So there are there are still these isolated exceptional dots, and then all the other stable objects will be here to the right. And I mean, where does this parabola come from? Well, actually, it was always there. We just normalized it away with the with the definition of delta, of course. So this parabola really was always there. And now, I mean, what I'm doing so this is now for slope stable sheaves in coherent sheaves on P2 or coherent sheaves on X supported on the zero section. There's actually no difference to this question. And when I'm going from coherent sheaves to my category AB, what I'm doing is I'm shifting this whole part. Let me use a different color for this. So I'm shifting all this part. I'm multiplying this with -1 and moving it over here. And remember, we have to make sure that the positive real line does not get hit. So finally, the result is that let me erase this now. So ZAB comma AB is a stability condition if and only if, so nothing goes wrong in this picture. So in other words, if let's say I call this curve here gamma of t. So gamma of t has to intersect the real line and the positive real line. So gamma of t, gamma intersect real line has to be in the positive real line. And I also have to make sure that no z of e is in the negative real line for e exceptional. And then, of course, so using this explicit Rosier-Lepeltier result, this gives explicit fractal-like inequalities for A and B. So, I mean, the point I really want to make is just asking yourself for which central charges does there exist a stability condition of this form forces you to know the answer to this Rosier-Lepeltier question. So in other words, I mean, if someone were to publish a paper that gives a complete description of the space of stability conditions on a surface, then he or she would have solved the complete answer to this question for every polarization for which slopes and discriminants does there exist a slope stable bundle. Okay. And so let's go back what this means to the space of stability condition. So this result, what does this give actually? So this gives, I mean, when I look at this space of stability condition and then I fix a numerical invariance, then I always get a locally finite chamber decomposition that with respect to, so for the moduli space of stable objects of this class. So, and what we've done here with this describes one chamber of the space of stability conditions with respect to stable objects of class the skyscraper sheaf of a point. So, I mean, inside there will always be a chamber where what we've described is the chamber inside here, so that the set of all stable objects of this class is exactly the skyscraper sheaves that we expected. And then, of course, the natural question to ask next is what is the boundary of this chamber? So, if you want to describe a connected component of the space of stability condition, the natural next thing to do is to study the boundary. And I mean, just from this picture, it's clear that there are two types of boundaries, either where this where this fractal-like curve hits the zero, hits the origin in the complex plane, or where one of these red dots goes to the negative real line. And it turns out that only one of them is an actual boundary. The boundary is where z of e is in the negative real line for e exceptional. And indeed, so let's say here we have one of these exceptional objects. So if this moves here to the real line, and remember here at -1 we have the skyscraper sheaves of points. Then it turns out that the so of course there is a morphism from E to OX, and this destabilizes. It makes all OX semi-stable. Of course, that's what we a priori would have expected. The boundary of this chamber will always be given where at least some of the OX are semi-stable. And here it turns out that really all of them are semi-stable. And now comes the second time where I need to use a little bit of derived categories technology. Namely, when E is exceptional, then there's always in the setting of a local Fano surface, there's always a spherical twist or Seidel-Thomas twist associated to this object. And so by studying this boundary a little bit more closely, is that so crossing the wall, this wall associated to E, so this makes all the OX unstable, but this makes STE of OX, so this Seidel-Thomas twist applied to the skyscraper sheaf of points stable. And then one is basically done. Then one has described the whole connected component, because of course we can characterize all the stability conditions where STE of OX is stable by just applying STE to our original construction. And so so let me call this set here U. So it follows that the translates of this chamber together with its boundary, so of U bar under the spherical twist at the exceptional vector bundles, so under the generated subgroup cover a connected component. So let me call this sub dagger of X. Okay, and so I mean this group of autoequivalences out dagger that are defined in the beginning are just the autoequivalences that preserve this connected component. So this is a subgroup. So this is the subgroup preserving sub dagger of X.
Can I ask Arend also, is this really the first point in the discussion where it's important that it's local P2 and not just P2 itself?
Yeah, that's correct. So I mean, so the advantage of the local P2 is really that we have these additional symmetries in the derived category, these autoequivalences that do not exist for the P2. So, I mean, if we looked at this wall for just P2 itself, then we would walk into some completely algebraic stability condition to which I have no geometric meaning. Okay, and so maybe let me say just 2 minutes how one can now use this description to prove the theorems that I started with. So the proof of theorem 1. So let me repeat the statement. This was said that odd dagger is equal to gamma 1 3 cross Z cross automorphisms of X hat. And so there are two things that go in there. So I mean, first we have to identify the subgroup generated by spherical twist. And just to make things a little bit more compact, let me also throw in tensoring with the line bundle O of 1 on P2. And there are really two steps in identifying the subgroup. So the first one is that actually I only have to throw in a single twist, spherical twist, namely at the structure sheaf of P2. And where does this come from? I mean, this now really comes from this theory by Gorodensev and Rudakov of exceptional bundles and mutations on P2. So I mean, the statement in here is that if I start with this, then I get all line bundles as exceptional objects in this group, spherical twisted line bundles. Then I get spherical twisted all mutations of them, and so I generate a whole group over here. So this really uses Gorodensev-Rudakov. And then that this is equal to gamma 1 3 is really a fairly simple computation. So one just has to show that these two satisfy the relation that the two standard generators of gamma 1 3 satisfy. And
is it obvious that they don't satisfy any further relations supposed to just show a quotient?
yeah, so the gamma 1 3 really appears here quite natural. So SL2Z appears quite natural because so as I said, the K group is three-dimensional. The Euler form has a one-dimensional kernel. So really the group of automorphisms of the K group is naturally SL2Z, and it's really this it embeds into SL2Z. So it acts faithfully on the K group. And so let me also say a few words about theorem 2. So remember, this was this embedding of the universal cover of the moduli space of elliptic curves with gamma 1 3 level structure to stub of X. So really it goes into this connected component. So how does one even define this map? So defined on a fundamental domain. Really explicitly we write on functions a of t and b of t. So this fundamental domain gets completely embedded into the set U that's completely described by these two parameters a and b. And so we write these functions a and t and b of t. And where do they come from? I mean, of course, we didn't guess this but stole them from the physics literature, so stolen from I guess the first paper studying this was Aspinwall-Morrison. And in particular, they also computed the monodromy of these periods. So these are periods of a meromorphic differential form. And I mean, they already observed that the monodromy action on the periods of this differential form matches this gamma 1 3 action on the level of K groups. And so all we are doing is then to lift the monodromy computation from the K group to these autoequivalences of the derived category. Okay, so in the last part of the talk, I just want to make some comment. What this whole picture here has to do with what I call the lack of birational geometry of X. And so, let me describe a conjecture and maybe for this conjecture it's most convenient to assume that X is a projective Calabi-Yau threefold. And again, I look at the space of stability conditions. And again, I look at the chamber decomposition of stability. So with respect to stability of objects of class as skyscraper sheets of points. So with respect to stability of objects of class or X. And so let's say maybe let me call Cx the set of chambers that appear here. And then of course the group of autoequivalences acts on the set Cx. And the conjecture that one would expect is that there are finitely many orbits with respect to this group action. And each of these orbits has a very geometric meaning. Namely one for each Calabi-Yau 3 X twiddle that is birational to X. And so in other words, if we if you fix this class and we start with the stability condition where the skyscraper sheets of points are the only stable objects of this class, then when we walk around the space of stability condition, there are just two things that can happen when we hit a wall. So either we hit one of these birational walls where the moduli space changes, and I get as the fine moduli space of objects of this type, I get this Calabi-Yau threefold X twiddle that's birational to X. Or what could happen that all objects become unstable and they get the moduli space stays the same, and I just apply a derived autoequivalence to every object. And of course, in the when X is the OP2 of -3, then there are no birational objects, so there are no birational partners there. But already when X is the local F1, then so F1 contains a -1 curve, and if I do the same construction here, so I take the total space of the canonical bundle of F1, then this becomes a -1 curve. So the -1 curve C inside F, this is a -1 curve inside X. And so there is a flip at this curve, and actually one can induce this flip by, so one can induce this flop, the flop at C. By changing stability conditions. And I mean the flop is actually a funny picture because it has as a compact subvariety something reducible at P2 and a line sticking out. And one can really show that this so this happens in the space of bridge sensibility condition, that when I cross this wall, then the new moduli space becomes this irreducible space. And actually, so I mean this is how do I know this works? I really know this from discussions with Alistair Crow, with whom I discussed that one can see this using quivers and GIT stability. And so, I mean, this is the general picture one should expect. One, in this picture in particular, we expect that there are just two different type of chambers, one for this local F1 and one for this reducible thing. And all others should be translates under the group of autoequivalences. And I mean, in theory, if one had stability condition on projective Calabi-Yau threefolds, then this is the picture that would hope for also in the projective set.
So when you say there are no x tilde, birational to x, of course these are all rational, right? So do you mean there are none so that the graph of the birational map is proper or something?
No flops.
I mean, yeah.
No flops. He wants
I mean, every local Calabi-Yau
relation between
three
X
that's
and is crepant.
yeah, every local Calabi-Yau threefold that's birational to this one is actually isomorphic to this one.
They're all rational.
Trivial canonical class.
Yeah.
Yeah. Okay. So maybe let me stop here.
Questions? Seems not to be the case, and let's thank the speaker again.